Have you ever wondered why training large language models is such a massive challenge? The secret is the enormous amount of high-quality data these models need. But getting that data is incredibly tough. While many people have tried to solve this problem in various ways, one of the most promising approaches is using synthetic data. It's less expensive than other methods, but it does have a major drawback: the lack of diversity. Recently, Nvidia's new LLMs from their Nemotron family of models have addressed this issue. They've shared a pipeline for generating synthetic data that's used for training and refining large language models. This is Louis-François, co-founder of Towards AI, where we build and share educational content like our recent book or free videos like this one. And in this video, we dive into Nvidia's key learnings and insights for training an LLM using synthetic data. The first step in creating a synthetic dataset is to generate synthetic prompts. And for that, they built a model generator. One of the big challenges with synthetic data is its lack of diversity from these prompts generating new content. To tackle this, Nvidia controlled the prompt distribution to cover a wide range of scenarios thanks to a few tricks. But first, allow me to take a few seconds to talk about the sponsor of this video, OVH Cloud. With their new AI endpoints, a game changer in AI integration for businesses. This solution makes it incredibly easy to add powerful AI capabilities to your existing systems. Enjoy fast and reliable AI performance, perfect for real-time applications like chatbots, image recognition, and data extraction. Access the latest open-source LLMs including Llama 3 and Mixtral 8x22b, which I covered in a previous video, to power your applications with cutting-edge technology. Their platform is designed to scale effortlessly, handling everything from small tasks to massive workloads, which, as you saw from my recent book, requires tremendous work. So that's pretty cool. Plus, OVH Cloud ensures that our data stays safe with their commitment to top-notch security and data privacy, which is a big concern for many companies. Boost your business efficiency and stay ahead of the curve with OVH Cloud AI endpoints. Try it out now with the first link in the description below. Now, back to Nvidia's best prompts for generating this synthetic dataset. The first thing they used was a method called iterative weak-to-strong alignment. It starts with a strong initial model to produce synthetic data, which is then used to train a new, better model. It will be like using GPT 3.5 to train GPT-4. This process repeats in cycles. Each improved model generates higher quality data, which in turn generate an even better model. We will basically go from GPT 3.5 to 3.6 to 3.7, etc. This continuous loop of data generation and model training results in progressively stronger models. Every improved model is then used to create prompts for data creation for training the next one. Okay, so that's cool and all. We've got a way to create better models with little manual data improvement work, but how did they fix our prompt distribution issue? Well, they've used several prompt engineering techniques, which we also cover in our book Building LLMs for Production, with more essential insights for training and working with LLMs. But the first technique they used is the single turn prompts. Here, a generator creates various macro topics such as artificial intelligence or climate change or ancient civilizations. Each of these macro topics is divided into subtopics. For instance, under artificial intelligence, subtopics might include machine learning, natural language processing, and ethical considerations. Questions are then created for each subtopic. There are two types of questions: open Q&A prompts and closed Q&A prompts. Open Q&A prompts involve questions that require a response generated from understanding and integrating information from a large context of multiple sources, such as how does natural processing enhance human-computer interaction? Or what are the ethical implications of deploying AI in healthcare? Closed Q&A prompts involve questions that have specific, definitive answers that can usually be directly retrieved from a given text or dataset, such as what year was the first programmable computer invented, or what is the greenhouse effect. For open Q&A prompts, the generated questions are refined to make them more specific and detailed. For example, a general question like what are the applications of machine learning might be refined to how is machine learning used to improve the accuracy of weather forecasts. For closed Q&A prompts, they use the C4 dataset, a continuously updated web data collection prediction. Each document from this dataset is fed into the generator, which produces an instruction specific to that document. The document is then concatenated with the instruction using specific manual templates. For example, for a document about machine learning, the instruction might be summarize supervised learning and describe how decision trees are used in the real world. Apart from single-turn prompts, the model needs data on how to follow specific instructions and how to answer in a way that meets the user's requirements. This brings us to the next two important types of prompts: instruction following prompts and preference data. Let's look at them one by one and explain why these were useful for diversity in training data. What is instruction following? It's when the model understands and executes specific instructions a user gives, ensuring the model aligns with the user's expectations. In Nemotron's case, its own generator, or the current best model, creates these instruction following prompts, each paired with a general prompt. For example, if the general prompt is write an essay about machine learning, the instruction prompt might be something like your response should include 3 paragraphs, assuming the answer in your dataset has 3 paragraphs, obviously. This pairing helps the model deliver responses that meet specific user requirements automatically. You just basically describe your dataset that you already have. Here, an interesting variation is multiturn instructions, where the instruction applies to all future conversations. For example, if the multiturn instruction is answer all questions with detailed explanations and examples, and the user first asks what is the significance of the Turing test, the model will provide a detailed explanation, including examples. If the next question is how does the Turing test apply to modern AI, the model will continue to follow the instructions and provide a similarly detailed response with examples. So in this case, it makes the model keep the same style of explanation. Now for the third technique, preference data. Preference data involves synthetically creating two-turns prompts to help the model learn and adapt to user preferences. For instance, we use a user prompt from ShareGPT, a platform where users share their interactions with AI models. Let's say the user prompt from ShareGPT is "What is the meaning of life?" Explain it in 5 paragraphs. The model then generates the assistant's response. The meaning of life is a philosophical question that has been debated throughout history. It's a complex and multi-phase topic, and different people may have different answers, and etc. Based on this response, another reply is generated and labeled as the user's response, such as "Shouldn't it be 42?" This cycle helps the model learn to anticipate and respond to user preferences. In this case, it's to be funny or just share the 42 meme. Even if this one might not be that accurate, it surely adds meme potential to the LLM. To ensure that the response differ from one another and maintain a realistic dialogue, the model is given clear role descriptions on how to provide answers when replying as either the assistant or the user. For example, as the assistant, the model might be instructed to provide detailed, informative answers, while as the user, it might ask follow-up questions that seek further clarification or additional information. We've now discussed single and two-turn conversations with the model, but in real life, our conversations with the model usually go back and forth multiple times. To handle these longer interactions, we use a method called synthetic multi-turn dialogue generation. Here, we assign the model 2 roles, one as the assistant and one as the user. The model receives specific instructions for each role and starts with an initial prompt, such as a question or statement. It then alternates between these 2 roles, creating responses back and forth, simulating a real conversation. This process helps the model learn to manage extended dialogues by practicing both sides of the interaction. However, this approach is risky as it can enter boring repetitive loops and return to our initial data diversity problem. From all these prompting techniques, the next step is to ensure that the model delivers the correct response in a way the user wants and stays diverse. This is called preference fine-tuning and is based on the correctness of the response. To generate this, we need a prompt and its associated correct and incorrect response. For example, if the prompt is explain the process of photosynthesis, photosynthesis, a correct response will accurately describe the stages of photosynthesis, while an incorrect response might provide unrelated or incorrect information. If you remember earlier in the video, we said that different prompts have been given to multiple intermediate models that generate responses to train the next model. Using multiple models creates a more challenging synthetic dataset. This helps ensure the diversity of the data, as each model may generate slightly different responses to the same prompt, reflecting a broader range of perspectives and styles. We can use ground truth labels or a model to determine if the responses are correct. Ground truth can be based on existing dataset labels or validated using tools for Python or mathematical tasks. For instance, for a prompt related to solving a math problem, the ground truth label would be the correct answer calculated by a verifier. We could use an LLM or a reward model as a judge for model evaluation. For example, if we use an LLM, we generate responses from two different intermediate models and compare them. To avoid positional bias, we swap their positions and compare the responses again. It was also observed that reward models perform better than LLMs as judges by differentiating the responses more accurately. For instance, the reward model used here, Nemotron 340B reward, shows higher accuracy in evaluating responses in complex scenarios, such as distinguishing between nuanced and straightforward answers to technical questions. This approach not only ensures the correctness of responses, but also maintains a diverse set of high-quality training data, enriching the model's ability to handle a variety of queries and instructions. TLDR, we can see how important more advanced prompting techniques are, especially as we are building increasingly integrated systems independently training thanks to autonomous LLMs working together. Synthetic data training offers a promising approach to developing models that are not constrained by data bias, quality issues, or high costs. I hope this overview into synthetic data generation has provided valuable insights into how data can be generated for custom domains and how Nvidia has done it with their Nemotron family of models. If you're interested into learning more about how LLMs are used in real-world applications and their broader impact, be sure to subscribe to the channel and check out our new book, Building LLMs for Production, where we discuss the crucial steps in depth with practical examples. Thank you for watching, and I will see you in the next one.